Yes, you're in the right place. It's Boritzer's Bio Briefings where you're hot and we're not. And welcome once again. We have great guests, a great show today scheduled for you, and something that certainly will involve you. Even though you may not know it now, you will at the end of today's interview. We're going to be asking some student learning outcomes, some fact-checking at the end of the broadcast. So please pay close attention to our guest today. I'll introduce him in a minute. Let me just lay out the student learning outcomes. 1, does size matter? Number 1. Number 2, can you live forever? Number 3, 5 things that your wife wanted to know about telomere research but was afraid to ask. And one more is, what does telomere research and Cyrus Miley have in common? At the end of today's interview, you'll be able to answer all those questions. Let me introduce, without further ado, my special guest today. My guest is Professor Richard Allsopp. Professor Allsopp is a molecular biologist. Is that a general term, or perhaps refine it for us?
More so specializing in telomeres and telomeres and aging.
Telomeres, okay.
Yeah.
Okay, and we'll soon get into what general area. It's obviously not podiatry or chiropractic.
No.
And it also has nothing to do with vitamins.
No.
No. Okay. No. So let's dispel some common myth maybe associated with the word telomere. And I'll let you go without further. Why don't you tell us a little bit? Oh, I'm sorry. I forgot to give you affiliation. Professor Allsopp is with the University of Hawaii, John A. Burns School of Medicine. And how long have you been there?
Been there 10 years.
10 years?
Yeah.
And his research is world famous, stretching all the way from Europe to Asia and everything else in between. So why don't you tell us a little bit first, what is it?
Are what cap the ends of chromosomes. So every human cell has 92 chromosomes. And to stop the DNA from unraveling, it's capped by this genetic element called a telomere.
Okay, you got me. Hands up. Okay, I surrender. Because there might be some people out there who are not familiar with the concept. I mean, we've heard a lot about the words chromosomes. We've also heard about the genetics. We heard in the past double helix. Perhaps you would be kind of just explain to our audience really what are we talking about? What are chromosomes? Obviously, they're never advertised in Cosmopolitan magazine, to my knowledge. I may be wrong.
Right. No, I don't think so.
Okay. So a little, perhaps just a preliminary biology lesson to bring us up to date to genetics.
Sure. So the genetic code in all our cells is packaged into chromosomes. So the chromosomes are the basically big chunks of the genetic code. So there's 6 billion nucleotides in the human genome. So every cell.
Explain what is a nucleotide and what is a human genome.
The nucleotide is the building block of DNA, and the genome is what encodes all of the 25,000 genes that make the proteins that make us.
So we're composed of 25,000 pieces? That's what you're saying?
25
categories,
25,000 genes.
25,000 genes.
genes.
And you're telling me that each one of us, if we were to dissect and put us under a microscope, our genes would look different from each other.
They would look 99.99% similar.
Similar. Okay, so where are they? So they define what? Do they define our color of our skin? Do they define the length of our hair?
All of that. They define everything about you. Everything. Including how fast you age.
How fast? So that means when we're talking about the chromosomes and we're talking about the 25,000 genes, we're talking about every facet of your personality, your brain matter, anything that we can measure chemically or electronically or by sight. How would we be able to identify these specific genes? How could we look at them?
I mean, there's different ways that people look at genes and analyze what they express. So each gene encodes a protein, and the proteins, go and associate with each other, and they have functions in the cell. Some of them are membrane proteins on the surface of the cell. Some of them are interior to the cell. Some of them are excreted by the cell. So, and then different cell types, 200 plus cell types that compose your body, each express a different subset of these genes that make up the human genome. So not every cell in the body expresses all 25,000 genes. It varies depending on what tissue you're talking about, brain or heart or lung. They all express a different but overlapping subset of these genes.
So with the discovery of being the deciphering of the human genome, which I think happened about 15 or 20 years ago, am I correct in the time frame?
Yeah.
Yeah. So with that, what did that really mean to scientists? That we were able, what did it mean in practice? Were you able to somehow code each gene, give it a amino acid designation or some kind of a designation, give it a letter code? How did that work out?
Well, sort of a complex question actually, because some of the genes had been identified prior to the entire sequencing of the human genome and had already been given names, but then there were many that were not, and they were all given separate codes. They're generally classified into families.
Okay, can you give us an example of some of those families?
Sure. One family might be genes that include structural components of the cell, like the fibers, collagen fibers, components of the cell membrane, components of different parts of the cell that give it the shape that it's in, like actin filaments, myosin filaments in muscle, or these kinds of genes. They're sort of would be classified in one family, and then you have other types of genes. Another class is transcription factors. So that's an important class of genes, and that family encodes genes that are responsible for driving the expression, turning on or off the different genes in the body. That's what the transcription factor does.
So when you're talking about turning on and off, I don't know, for some reason, I get this parallel universe of like code for a programming code for computers. When you say turning on and off. So is there some relationship to being able to decipher the human genome and the fact of where we are in the development of perhaps electronic coding and so on?
I don't know about that.
So it's not as simple as an I, 0 and 1
Not
code.
quite.
Okay.
Not quite. No. It's a little more complex than that. I mean, I would think of it more of a lock and key mechanism, where each gene has a set lock, and it requires a set group of these transcription factors, which would form the key to bind to it, and that will either turn it on or it'll turn it off.
Now, the basic components of the genes that you're talking about, is there some way of categorizing them? Do they have some kind of a coding?
Well, they're classified, as I was saying before, more in terms of their function. So transcription factors have a specific function, turning on or turning off genes. Structural proteins have a function of, giving the cell the shape that it has, and then there's other. So that's more how the genes are categorized.
So there's no code like 4 letters or a letter T or G or anything, combinations of that type that give it like a dictionary that you could look up.
Well, I mean, there's structural motifs that are in different genes. So transcription factors sometimes will have a motif, like a DNA binding motif, that might be in common to many different types of transcription factors, and that other genes of other family members don't have, and that's what allows it to bind to the DNA. So there would be a set of the nucleotide building blocks, a sequence that encodes this motif that allows it to bind to the DNA.
Okay, so when we talk about the double helix that is often shown in all kinds of advertising for health or for research, what is that actually showing us when they show the 2 strands? Are those pictures of a set of molecules together, a set of cells together, a set of genes together?
Those are a set of molecules that are together. So you have a strand on one side and a strand on the other side. They're both composed of long stretches of these building blocks, these nucleotides. And then you have complementarity. You have the C cytosine binds to guanine, adenine binds to thymine, and they sort of pair up that way.
And where does the telomere fit in?
It fits in at the end.
At the end, so it's at the end of the strand.
It's at the end.
At the end, okay.
Yeah.
So, can you show us a picture of what that looks like? Ah, there's two telomere genes on a date. Or perhaps they're being compared, father and son. Or perhaps someone who's going to live long and someone who isn't. Or someone whose traits are being refurbished as we speak. So, on the right side, it obviously looks like a gene with very short telomeres.
Yes.
And on the left side, we're looking at a gene with long telomeres. So, what in essence does that mean for the average person?
Well, I mean, what it means, what we have shown that it means to date is that if you have short telomeres, the cells in your body will not be able to live as long as the cells in your body that have long telomeres. So it dictates the cellular life, especially the cells that divide a lot, that turn over a lot, like blood cells and skin cells. So if those cells have shorter telomeres in one person, or the same person over age, then those cells will not be able to divide enough and replenish that tissue as well.
I see. And what can we use to replenish them?
Well, there's an enzyme called telomerase, which binds to the end of the telomere, and that's what functions to extend the telomere. That's the only enzyme in the body that can do it. So if there's no telomerase in the cell, what happens is that telomere gradually gets shorter and shorter and shorter. It sort of erodes away as these cells continue to divide and make more skin or make more blood. The telomeres continue to erode because there's either not enough or no telomerase in those cells.
We live in a society that constantly wants to have answers, to problems. We live in a society where we think there must be an answer to almost every issue that is raised. So, are you born with this tendency, with this replenishment of this particular enzyme in your body? Is that like preset?
Well, it starts out high. It starts out really at high levels, very, very early in embryogenesis, and then, gradually as the cells during embryogenesis, the cells develop. You get different organs being formed in the newborn, and then after birth, the amount of telomerase in the body gradually decreases until by the time you hit adulthood, there's only a few rare cell populations that actually have high detectable amounts of telomerase in them.
I see. So if we are interested in continuing this rejuvenation process, in maintaining a situation in situ that will keep replenishing, at least trying to retard the aging factor of the cells, then either we have to, I would believe so, that we have to stimulate the body to produce more enzyme, or somehow prevent the degeneration of the enzyme producing mechanism.
That's right.
So,
That's right.
So where is the focus of the research taking place?
Well, the focus of the anti-aging research is to try to find ways to turn on telomerase. So, there's been a lot of studies done where they can actually genetically input the telomerase gene into cells that don't have it and turn it on artificially and show that is enough to not only stop telomeres from shortening and extend the telomere length, but it actually stops the cells from senescing. So senescing means the cell can no longer divide. It's reached the end of its lifespan. That doesn't happen if you reintroduce telomerase into these cells.
I see. Well, hold that thought. We're going to be taking a break and give our sponsors a chance to make themselves heard. Stay tuned. Don't go away. We are with Professor Richard Allsopp from the JAB School of Medicine at the University of Hawaii.
I'm Jay Fidel. That's Sharon Moriwaki of the Hawaii Energy Policy Forum. And every Wednesday we have Hawaii, the State of Clean Energy. We've been doing it for some time now, and we have some fantastic guests on there, unbelievable guests who give us insight into what is going on in a very complex, sometimes very confusing, sometimes very disappointing area of progress in the state. So we love doing this. We love meeting them. We love talking to them. We love having their ideas out on the table. So maybe, just maybe, we can all make some sense of what's going on. Sharon, what do you think?
I think that's absolutely correct. We enjoy ourselves meeting with all these people and hearing about the energy and the state of clean energy, and hopefully we advance clean energy for the state. So it's terrific. Join us.
Okay, it's every Wednesday. Okay, Wednesday is Energy Day. Every Wednesday, 4 to 5 p.m. Hawaii, the State of Clean Energy, here on ThinkTech Hawaii.
We're back, and you're watching Boritzer's Bio Briefings right here on ThinkTech Hawaii. And we are very proud to have our guest today, Professor Richard Allsopp of the JAB School of Medicine at the University of Hawaii, with a specialty that is very unique, and those are telomeres. And we're getting a little background on the telomeres. What do we need them for? Why do we want them hanging around? And what of use are they? What do they do productively? But before we do that, I'd like to have Professor Allsopp talk a little bit about the whole history. How did this subject come about? And was it possible before the discovery of the human genome to be able to research these particular issues?
Sure. So telomerase, the enzyme that is essential to maintain these telomeres, was discovered not relatively recently, back in the early 80s, in an organism called Tetrahymena thermophila, which is a pond ciliate. It's one of these ciliate protozoan single-cell organisms, and what's special about that this organism in terms of telomeres and telomerase is that its DNA, human DNA, has 92 chromosomes, as mentioned before. Mm-hmm. The Tetrahymena thermophila has thousands of mini chromosomes, so they have many more telomeres that have to be replenished in order to allow these cells to continue, these organisms, mm-hmm. single-cell organisms, to continue to proliferate. So they have lots of telomerase, much more than any human cell does at any point, many times more. So this enzyme was first detected in this organism based on its ability to, and this was all work done in Liz Blackburn's lab, who got the Nobel Prize for the discovery of this enzyme in the 80s. So it was discovered based on its ability to interact with what's called an oligonucleotide substrate, which means that this is a short strand of maybe a couple dozen DNA building blocks, nucleotides, that telomerase can recognize and bind onto if it's there. So if telomerase is there, it'll bind onto it, it'll extend it, it'll add, what they found is that it will add a sequence that is exactly the same as the sequence of the telomeric DNA that is at the ends of the chromosomes of the Tetrahymena thermophila.
Wow, what an exciting discovery it must have been, especially we're looking back in 1975 or even earlier when she came upon this discovery, aren't we?
Well, the hardcore molecular biology, which I just described with the oligonucleotide and extensions, that was more done in the 80s. But the initial indications that this enzyme would likely exist, which was based on all these mini chromosomes that this organism had, and all of the different telomeres, was done a little bit earlier. So telomeres were discovered before telomerase enzyme was.
Well, give us a little perhaps relationship between telomere length and some of the diseases that we are familiar with.
Well, there's a few that have been discovered. What happens? Let me back up and just talk a little bit about what happens in mice. If you delete the telomerase gene from mice, they can't maintain their telomeres anymore in any cell. So what happens is eventually, as these mice reproduce and make young mice, and those young mice go and breed with other mice and make new mice, a second generation of mice. And if this is all done with no telomerase, then what happens after about 4 or 5 generations of these mice, they start showing accelerated aging phenotypes, and they can't reproduce anymore because all of their cells are sort of senescing prematurely. So they have gray hair, they are less mobile, they're less active, they have a lot of the aging-like phenotypes.
It sounds like almost a subject of a horror movie. I can see this like a late Saturday night, and you're watching people aging within 2-3 years. And if this is replicated from the mice in human behavior and human biology, then we're in deep trouble.
Yeah. Oh, yeah. You would be.
So, go ahead.
So there's been no human, to my knowledge, that's been identified that has no telomeres in them, because I think mice are unusual in that they have really long telomeres, and so they can actually go 4 or 5 generations. But their telomeres are much longer than humans. So if human had no telomeres, I think it would probably be game over after
Birth almost.
Yeah, whether even if you have only half as much telomerase as you should have. So this is a disease which does exist. So dyskeratosis congenita is the disease that's associated with a mutation in one of the telomerase genes. So one set of DNA is inherited from the mother, one set of DNA is inherited from the father. If either one of those telomerase genes is defective, but one of them remains functional, that even that isn't enough to prevent the more rapid erosion of telomeres than what would normally occur. And if that happens, then it's been associated with this disease called dyskeratosis congenita. So it's quite rare, but it was the first one to be associated with mutations in telomerase.
Well, how does this affect cancer, though, specifically?
Cancer? Well, cancer is sort of the other side of the coin. Cancer are cells that have lost their ability to divide indefinitely. So now that doesn't have anything to do with telomeres. That has to do with other genes in the cell which control how fast a cell divides and whether it's responding to the right cues to stop dividing under the right situations. But what happens a lot of the times in cancers, certain types of cancers at least, is that telomerase gets turned on. In fact, it has to get turned on in order for a cancer cell to continue to divide and divide and divide. So roughly 85 to 90% of human tumors that have been looked at so far have reactivated in one way or another this telomerase gene to allow cancer cells to continue to proliferate.
Oh, so it's actually a double-edged sword here we're talking about.
Well, yes and no.
Okay.
Yes and no. Telomerase itself in humans has not been shown to be oncogenic, so meaning that it's not cancer-causing itself. You can put telomerase into cells, as I was mentioning before, skin cells, which have no telomerase, normal human skin cells, they can become immortal, but they won't form a cancer. They will just continue to divide and divide and divide, but they won't divide uncontrolled. They will.
I see.
They will, if the cell is damaged, or if it reaches a certain number of cells, then the cells will stop dividing on those cues. A cancer cell will not, because other genes are mutated.
Oh, so it's actually almost a sidebar to the discussion, because it's really the therapeutic effects from the telomeres is not evident in terms of controlling the cancer.
Right. Right. No, well, actually, right and maybe not right. I mean, there are telomerase inhibitors that have been identified that could stop a tumor, at least certain tumors. Because the odd thing about tumor cells is that they have telomerase, but they don't have long telomeres, most of them. Some tumors do have long telomeres, but most keep their telomeres the same length, but it's a very, very short length. So if you were to inhibit telomerase in those cells, they would all quickly die. Now, you can't, so you can imagine a patient taking a telomerase inhibitor, it would affect all the cells, both the tumor and the cancer cells, but the cancer cells would theoretically be most susceptible because their telomeres are already so short. If they divided even once,
they would
gone. Senesce.
There'd be history.
Yeah.
So it's almost a Hobbesian choice. And the titration of this kind of, how should I say, tonic or therapeutic agents or whatever, really is a almost experimentation type of approach to a patient treatment. I mean, it's not something that you can get a medication in the drugstore or get a drip or an IV, and somehow you'll go and be just perhaps half an hour a day.
Not yet. There's companies out there that are on the road, fast track to trying to market some telomerase inhibitors to treat cancer, but it's not a popular therapy at the moment.
Okay, and tell me a little bit about the type of how should I put it? The type of technology necessary to do this kind of research. Is there a specific kind of microscopy, electronic or otherwise, that enables this type of research?
Yeah. Well, to detect telomerase, there was what they call an assay. So enzymes are the activity of an enzyme is measured by what they call an assay. And the telomerase assay was invented about 20 years ago, and it's based on a technique called polymerase chain reaction, PCR. So it's just, we talked about before that you have the oligonucleotide, which telomeres can bind to and extend and add telomere repeats onto. So you mix this oligonucleotide with an extract from the cells that you think have telomerase. And if it's there, it'll extend this oligonucleotide. If telomerase isn't there, nothing will happen. And then you can detect these extended products, which are very low in number initially. So you use this PCR technology to amplify those extended products specifically. And so if you get an amplified product, then you know telomerase is present.
Okay. Now, one of the questions, especially in the West, we're always looking for the next elixir, the next fixer. So take us 100 years ahead. Where are we going to be with telomeres?
I think that I think that you're going to have both good therapies to knock out telomerase, the enzyme in, or the activity of the enzyme in cancer, and also I think you're going to have good, safe and naturally derived compounds or extracts that have been identified that can rejuvenate telomerase in, especially as we age. And stop cells from senescing. In particular, the cells that are proliferating throughout our life, like the immune system, skin, and epithelial cells. So these cells are constantly turning over, and in the elderly, people have measured telomere length from these different tissues, and they get quite short. Especially once you hit around 90 or 100 years of age, telomeres are about the same size in the blood as you would find in a senescent cell in a petri dish.
So there's no way of waking them up?
There's no way of waking them up if the telomeres get that short, so you need to prevent it.
Or make them longer, one way or another?
Yes.
So since we know that those are the only possibilities with regards to telomeres, they know everything we are doing because they're watching us very closely. What is on the market there? What is going on in industry? Because we know that the pharma industry, the biosimilar industry, and the vegetarian organic industry, and perhaps Chinese medicine, and perhaps manipulation and chiropractic are all busy trying to figure out how to exercise these telomeres and get bigger and longer.
Not much, unfortunately. There's a handful of. There's a lot of stuff that you got to take it with a grain of salt. I mean, a lot of stuff that's out there is, questionable as to whether or not they have been scientifically proven to lengthen telomeres or not. There is a compound from astragalus, a root from China, which has been used to make an extract and sold under the label TA65, which now this has been shown to be effective at least stopping the erosion of telomeres, or possibly even lengthening the telomeres that are very short in a cell. So I think this is a good start. a good product that potentially could be used now. I think there's probably better ones on the horizon, but I think TS65 is a good one that that can stop the erosion of telomeres. And in fact, let me get back to telomeres and disease. Another disease that's been associated with mutations of telomerase, oddly enough, is pulmonary fibrosis. It's a lung disease. So it's been shown in certain individuals that have this, it's associated with mutations in a component of telomerase. There's two essential components to telomerase. There's a RNA component and there's a catalytic enzymatic component. So there's one's called TERT, one's called the RNA component. So mutations in either of those two components have been associated with pulmonary fibrosis. What happens is telomeres get abnormally short in the lung tissue and other tissues in these individuals. And so this led us to test out this TA65 compound in mice by inducing pulmonary fibrosis in a certain mouse strain that has a mutant copy of telomerase, so sort of to mimic the human phenotype that's associated with the disease. When you do this, you can actually, this compound is actually very good at reactivating telomerase in the lung tissue of these mice and suppressing the development of this pulmonary fibrosis in these mice.
So would the next step be possibly experimentation on primates?
Yeah, that could be a next step. Mm-hmm. Mm-hmm. And possibly even clinical trials. It's a safe compound. It's proven to be. It's an over-the-counter product. So
really?
Yeah.
So how come I don't see the lines in front of CVS, Walgreens, and Long's drugstores?
That's a good question. Marketing problems. It's out there. You can get it online. There's different companies that sell it,
but usually at that level, there's no follow-up and see, pre and post testing if it's just open over the counter. I would imagine.
Quality control. Yeah. That's true. Yeah.
So perhaps we should be looking at the bio industry out of China, perhaps sending it over to us. Mm-hmm. With some other compounds. Mm-hmm. Maybe we will be the guinea pigs. But one of the things that I wanted also to touch on is the use of predicting factor, using the telomeres in some manner of predicting damage to the body, in predicting longevity, in predicting demise, in predicting lifespans. Or perhaps even using telomeres to see of the efficacy of specific treatments or specific invigorating or reinvigorating agents.
Yeah, I think the telomere length, the size of the telomere, I think is a good marker for overall health. And again, there's been a lot of studies by Liz Blackburn's lab that have shown various kinds of stress and various types of illnesses are associated with a shortening of telomeres in people. And interestingly enough, if once the stress goes away, or once the disease is cured, telomeres can actually rebound to some degree.
So I'm just surprised. You're the only one in Hawaii who's working on this? I mean, how is this possible? We have 1 million people here. I would think there are at least 50 who are chasing right now the golden rainbow.
Yeah, this is true. I mean, if you could find a way to keep these telomeres long during the stressful time or during the time when someone is sick, I think that might lead to a quicker recovery. But we don't know that yet. There's been a lot of work that still needs to be done, and but I think it's going to be a good overall marker for health, I think, in the future.
Okay.
Yeah.
Well, we're going to stop on this point, and we're going to take a break, and we'll get right back to our special guest today, Professor Richard Allsopp of the UH School of Medicine. The way it looks, or?
Sometimes. Well, you know, you got the tissue cultures going on, and the petri dishes of cells, and then you have, if we have mice in another room that we're doing experiments with that might have mutations in telomerase, and then we have, you know, just different types of machinery, you know, on the bench. Nothing. It's really tough to describe what it is without actually seeing it, without actually seeing a visual of it. But it's a little bit of beaker pouring as well.
Okay. And can you see any aspect of your research coming into popular culture?
Popular culture.
Right?
Popular culture.
Can you see people, just like if I may use the analogy of tobacco smoking, which is harmful,
Yeah.
and with those vaporizers or whatever they're smoking now, instead of taking nicotine without the tobacco, do you see that the carriers of the particular telomere lengtheners, so to speak, could become part of popular over-the-counter sales?
Oh yeah, I think so. I think it definitely could be, especially once you get some competition going on who's got the best telomerase activator. Well, you know, we're a few years away from that yet. It still hasn't completely caught on as a common, certainly not a household word that's used as an indicator of health, but I think it's getting there. You know, slowly with time it'll get there, and you know, as some of these health products come, more and more of these products come on the market that can activate telomerase and keep the telomeres the nice and healthy. I think that'll become more popular, I think, with time.
Well, I can see then too, as we're talking about the business aspect of what you do in research, I would see only two things really. One is to get a device that drives the growth of telomeres or retards the demise of telomeres. That's number one. And number two, I would think, is the measurement to see if these lotions, potions, and motions actually have any effect in longevity, disease retardation, or cures.
That's right. That's right. So we have sort of scraped the tip of the iceberg with this TA65 compound and pulmonary fibrosis. Exciting results. I definitely would like to follow up with that, but I don't think that's the only disease that can potentially be treated, at least in part, by a telomerase activator. Like, for example, recently, heart disease. People with heart disease have been shown to have a much higher risk of having shorter telomeres.
Oh, really?
Yeah.
Well, what particular kind of diseases? You mean the diseases where the walls or of the arteries or vascular system is?
Vascular system, yeah. The cells that line the lining of the arteries. We don't know the full extent of all the diseases that are associated with or susceptible to becoming worse with shorter telomeres. But certainly pulmonary fibrosis and possibly heart disease as well. This is a very new study that's being released. Could both be candidates there.
Now, I know that your particular research has tended to focus on aging and the retardation of aging. I know that you're very active in following up research in the social sciences in aging and seeing what effect behavior and so on may have on telomere length. What is happening in the rest of the world in this particular field? Or is America the only area where this is taken hold as a serious pursuit?
No, there's other countries that are catching on. You know, there's telomerase meetings every once in a while, every year or so, and you get a lot of people from different countries come to these meetings, not just from North America, you know, Europe and Asia.
Well, we know there's a lot of this in America, especially. There is a whole industry of importing all types of how you call them, organic foods and special Chinese medicine, all sort of concoctions with all kinds of claims that are made, but most of them don't have any kind of scientific basis for comparison pre and post, or comparison with as compared to other type of treatments. Do you see that there's going to be a more structured regimen to evaluating the effect of any products or measurement systems that come on the market?
That's tough to say, you know. I mean, any decent product is going to have some scientific backing behind it. So, both, especially at the clinical level, at the human trial level. So, I mean, I think that's what people really should be looking for when they go to buy some of these products. It's not just to buy something because it's got the lowest price or a fancy label, but actually look to see that there's something that's on that, associated with that product, that it shows that, you know, it's got a real solid scientific claim backing whatever it's being proposed to cure. So I think that's what people ought to look for when they go to buy these products.
Well, I think we are, especially in the United States, but even worldwide, we are so affected by the rise of obesity rates in the population, and cardiovascular disease, inflammatory diseases, and diabetes, and everybody's looking for the panaceas instead of looking at the causation and how do we structure society that from early childhood until adulthood that will maintain certain behavior patterns that don't exacerbate the problem but rather prevent it from occurring. There was, I don't know if you remember, there was a product that came on the market just probably 5-6 years ago, Reversatrol.
Right.
Right. Now that was the cure for everything. Suddenly get rid of that belly, get rid of this, get rid of that, and you'll be healthy for life. And
right.
What happened to Reversatrol?
Well, it's still there. It's still there. I think it still has some real positive effects, but that's exactly what they are and are not. I think still has to be entirely delineated. But you know, it was first discovered based on its ability to extend lifespan in yeast. By activating this is a different gene than telomerase. This is these sirtuin genes, and involve in these energy sensing enzymes, so they can sort of kickstart these energy sensing enzymes and get your metabolism going, and potentially be used possibly to treat diabetes, but who knows? You know, the studies have to be done.
So how do you prevent the public from following blindly the latest news story that seems to have the answer of all of life's ills?
Well, you know, there's one philosophy is if something has a good indication that it has some longevity promoting abilities, even if some of them may not be entirely true or questionable, but at least if one or two are credible, then why not take it if it's safe to take? I think that's sort of a philosophy that's out there right now, and I think it's a good way to go as we begin to sort of extend our knowledge on what all of these different anti-aging compounds can do.
So a good caveat is really read, follow, look, listen, investigate, don't take on face value. Try to get your news from legitimate news sources. And if you have a friend like Professor Richard Allsopp, call him up and ask him, is this really true? On that happy note, first of all, the questions we had at the beginning of the show. Does size matter?
Oh yeah, size matters.
Size does matter. And did we answer the question what your wife wanted to know? 5 things about telomeres? Probably yes. And until the next time, you've been watching Boritzer's Bio Briefings. Our guest today has been Professor Richard Allsopp of the University of Hawaii School of Medicine. The subject has been telomeres, everything you ever wanted to know. This is a beginning of a long chapter, and hopefully with lots of successes along the way. And we're happy to have you here today with us.
My
Hope
pleasure.
you come again and report on some of the things that you've been working on. Until next time, you're watching Boritzer's Bio Briefings. Your host Rafi Boritzer, right here on ThinkTech Hawaii in Honolulu.